Thank you and welcome to my talk on ballistic impact on concrete slabs. My name is Martin Kristoffersen and I work as a researcher at NTNU together with Professor Tore Børvik. This work was carried out in collaboration with Oda Toreskås and Sumita Day from the Norwegian Defence Estates Agency. Concrete is by far the most used construction material in the world. It has many attractive properties and is used in almost any type of structure. This includes fortifications and protective structures for which high velocity impact is an important issue. In this study, we investigate the perforation resistance of 50 mm thick concrete slabs made from 3 different concrete qualities as listed. The outline of this talk will consist of material testing, ballistic impact tests, finite element simulations, and some concluding remarks. We begin with the material tests. We have conducted 3 types of tests: cylinder compression, cube compression, and tensile splitting as illustrated. All tests were instrumented with force measurements and digital image correlation. This was used to establish engineering stress-strain curves. Here are the results for the cylinder compression tests, the cube compression tests, and the tensile splitting tests. The resulting curves are averages of 3 tests each, and the strength was somewhat above the nominal specified strength. We now look at the ballistic impact or perforation tests. 50 mm thick concrete slabs of all 3 concrete qualities were cast. The slabs were impacted by hardened steel projectiles traveling at 120 to 300 meters per second. The tests were captured by 2 synchronized high-speed cameras, one for the impact side and one for the exit side. Here is a typical example of a perforation test. The cameras are used to measure both the initial and residual velocities, and we can observe the fragmentation when the projectile exits the slab. Then we plot the initial and residual velocities, and then decrease the initial velocity until the projectile is stopped. This is shown on the picture on the right. The data is then fitted to the Recht-Ibsen model and the ballistic limit curve is established. We repeat the exercise for all 3 concrete qualities and determine the ballistic limit velocity in each case. As seen, the ballistic limit velocity increases approximately linearly with increasing concrete strength. By using digital image correlation, we are able to track the motion of the projectile as long as it is visible. The dashed part of the line indicates the time for which the projectile is obscured. The finite element simulations were all carried out using LS-DYNA. We used a modified version of the Holmquist-Johnson-Cook concrete model. The model is elastic viscoplastic and includes pressure hardening, strain rate sensitivity, and load angle dependency. An axisymmetric model of the cylinder compression tests with 1 mm sized elements was used for inverse modeling to obtain the quasi-static material constants for all 3 concretes considered. Dynamic material constants were obtained from the literature. The resulting stress-strain curves from the inverse modeling matched the experimental data well. After calibrating the material model, a model of the perforation problem was set up using the same element size. As for the material tests, an axisymmetric model was used for computational efficiency. Friction was set to 0 to keep the model conservative. Here is an animation of a typical numerical result. The strain pattern shown on the fringe plot resembles the experimental observations, and the ballistic limits are well predicted. The results are on the conservative side as shown by the ballistic limit curves for all 3 concrete qualities. We observe that the numerical results are quite close to the experimental results, and that the ballistic limit curve has a slightly different shape when comparing the numerical and experimental curves. The linear trend is conserved, albeit with a different slope. Here we see an experimental velocity time curve as shown before. The dashed line indicates the duration for which the projectile is not visible. The numerical velocity time curve for the same initial velocity matches the experimental curve qualitatively, but is on the conservative side quantitatively. It is of course possible to tune unknown parameters like friction and strain rate sensitivity to match the experimental results, but there is no predictive power in that and is only included as a numerical exercise. Finally, a parameter study on the C110 concrete was performed. Various parameters were either doubled or halved, and their effects on the ballistic limit velocity was assessed. The entire range of initial velocities were simulated for all parameter variations. This is possible when utilizing axisymmetric models, which have a very low CPU cost. One simulation of this kind took about 20 minutes. First, we note that doubling the compressive strength gave only a modest increase in ballistic limit of about 4.6%. Having it reduced the limit by 9.4%. Next, doubling or halving the tensile strength, however, changed the ballistic limit about 23% in each direction. Further, omitting strain rate sensitivity reduced the capacity by roughly 20%, while doubling the strain rate sensitivity constant C increased the capacity by only 4.4%. We thereby note that it's important to include strain rate sensitivity in simulations of this kind. Further, including friction or changing the material density resulted in modest changes in the ballistic limit velocity of around 3 to 5%. To round off the presentation, we note that the digital image correlation provides very useful measurements and enables us to calibrate the material model properly. The ballistic limit velocity of the 50 mm thick slabs increased approximately linearly with increasing compressive strength. High-speed videos enable measurement of both the initial and residual velocities, and even tracking the change in velocity as long as the projectile is visible. The finite element simulations, despite being axisymmetric and not full 3D, gave reasonable predictions of both the cylinder compression tests and the perforation tests. The simulations suggest that the tensile strength dominates the response of thin concrete slabs where there is little confinement. All the simulation results were on the conservative side of the ballistic limit curve. Finally, a few words on our current work. We have recently performed tests on 100 mm thick slabs, where we also included test series with reinforcement. The strain rate sensitivity in the material model used is symmetric with respect to compression and tension, contrary to experimental findings, so we hope to ameliorate this in the future. Investigating other material models is of course also of interest, and using full 3D becomes necessary when reinforcement is included. Thank you for your attention.